One particular way in which I'm currently thinking about a possible implementation is derived from an idea of how cortical columns are working. So the idea is that the cortical columns are arrangement of neurons that get trained to approximate particular functions, and they are on top of a state machine that sends control messages that can turn these columns into different states depending on their role in the architecture at any given moment. In this way, you get areas where the cortical columns are tightly coupled, and then you have different areas that form hierarchies and allow you to have different domains of perception. So some of them might be contrast features and color features, and others might be geometrical features, and the geometrical features are combined from textures that you bind in a particular way at a higher level. And so you can build a cognitive architecture or imagine that it's self-organizing in such a way. And the units that allow this construction, I call them request confirmation networks, and basically every of these units is a small state machine that is able to inhibit or activate the other units across certain dimensions. As a result, you get self-executing scripts. And the goal is basically to build self-organizing, self-learning scripts that can executing themselves without any kind of external control. And they, in different nodes, have to have different states. So they have an untrained state in which they're just basically dormant and don't do anything yet. Then you have a training phase in which they are organized into hierarchical scripts to explain reality. Then you have a latent phase where they are already trained but are not bound yet in a particular scene graph into a particular representation of reality. Then you have a binding phase where you are looking at a scene and try to make sense of it, and it organizes into some kind of dynamic computational architecture that exists in working memory and then can start to simulate reality. And then you have an initialized phase in which you start to look for particular objects and you start to make requests, and then these requests percolate across the children of the dependencies of these individual nodes, the different sub-features that need to be the case. And then you get back confirmations from these children. And when you succeed or fail, you need to repeat the process by either returning to the latent phase, depending if the scene has changed, or to the formation or to the binding phase. So this is a dynamic process that is basically computational architecture that continually runs. And it enables a hypothesis-based perception process. And hypothesis-based perception works bottom-up, top-down. So bottom-up, there are certain things in your visual field or in your proprioception that may be features of high-level objects that you don't know whether they're the case. But maybe you see a bunch of vertical structures and you know contextually that you're in a forest or in a parking lot. And depending on this, you may activate hypotheses for trees or for lanterns and so on. And then you actively look for features that can validate those hypotheses top-down. So you have a bottom-up queuing process that gives you a superposition of possible things that could be the case in the world, and then you go top-down and try to collapse these superpositions. And if you cannot get a match, then maybe you need to collect more information, so you start looking around and you get new perspectives and so on, you look more closely. And if this doesn't fail, then maybe you need to think harder, you need to resolve things, you need to get attention into how can I interpret this feature, what could this be? And if this doesn't click, maybe then you need to trigger learning behavior where you start to construct new scripts. And there are a number of challenges that we need to resolve if we want to get this to work. So for instance, the feature nodes need to represent their preconditions, and the preconditions have to be satisfied and propagated back to the requester. This is working. The same feature instance cannot be simultaneously bound multiple times. Right, so you every feature that you are looking at, for instance, if you see some blob of color in your visual field and you decide, okay, this is part of somebody's laptop or somebody's bottle and so on, it cannot be part of anything else. Right, so you carve up the space in such a way that all these features that you're observing get assigned to something in the right way and not multiple times. And often you need to have the same white rectangle multiple times in your field of vision. So you need to create multiple instances of it and make sure that they don't interfere with each other. And then this whole thing needs to work in such a way that you can propagate the requests back and forth in your graph in an overlapping way without these overlapping requests interfering with each other in the architecture. And the requests need to lead to dynamic anytime models. You need to get a result all the time, right? You need to be able to have continuous perception. So this request confirmation process cannot have infinitely many steps or very large numbers of steps. It needs to give you good enough results within very short numbers of steps that are periodically repeated, and in the process of periodically repeating them, get more and more accurate. And you have to be able to dynamically change the scene on the fly without this request confirmation process breaking down. If the scene changes, you need to be able to insert new objects, modify existing ones, and so on. So there are a lot of challenges that need to be solved if you want to solve this analytically, coding it by hand. So instead, what you should probably be doing is to define a search space for the correct architecture, and then let the machine do it.